Hi, ICSI 2021. I'm Jordan Hinkle. I'm a PhD candidate at the University of Wisconsin-Madison, and I'm here today to talk about Shipwright, a human-in-the-loop system for Dockerfile repair. And this is joint work with my colleagues Stanini, Leopoldo, and Marcelo, and my advisor Tom Reps. So I want to kick things off by talking a bit about Docker, since this is a work on Dockerfile repair. Docker is a tool for lightweight virtualization, and at a high level it helps developers do things like continuous integration, set up reproducible development environments, and deploy their software to cloud vendors. Of course, it does many more things. For me personally, I use Docker a lot to distribute research artifacts and the environment that goes with them. But at a lower level, Docker has some kind of core components. There are Dockerfiles, which is a source level artifact. There are Docker images, which you build from Dockerfiles. And then there are Docker containers. You can run containers from an image. And a good analogy here is source code executables and processes. You can look at building source code and getting executable. You can look at running one or many processes from an executable. And this is similar to Dockerfiles, images, and containers. So to drive this home, here's that analogy again between source, executable, and process, and a Dockerfile, a Docker image, and a Docker container. In this paper, we're interested at kind of build time. So we're not interested at runtime, anything dynamic, what's happening when containers are running. We're interested in this build step when you go from the source level artifact that is a Docker file to a Docker image. And in particular, we're interested in the cases where you're trying to build a Docker image from a file and things break down, the build fails. In those cases, hopefully we can pull off some automated repair. So here's a concrete example. This is a Docker file. It's kind of a reduced, contrived example of a Docker file, but it's also a broken Docker file because if you were to try to build this, you get this error. And it's not broken for trivial reasons. The syntax is fine, everything looks all right, but if you actually try and build this, you get some error about some sort of version mismatches between bundler and Ruby, and I'm not a Ruby expert, so I don't know precisely what's going on here, except that some of the versions are wrong. So we've seen a broken file, and now let's look at the fix. The fix in this case is actually quite easy. To fix this file, all we need to do is change a version number. Instead of version 2.2, we need to use 2.3.0. And if we do that, you'll find that indeed fixing the Docker file lets us successfully build an image. So now the question is, if we've seen broken files and we've seen some fixes, how often are broken files really an issue? And can we find a way to automate this process? So when we look out in the wild at public GitHub repos with 10 or more stars, we find that about 1 in 4 Docker files from those repos fail to build. And of course, there are some qualifiers on this. So we start with a data set from a previous work from Binnacle at ICSI 2020. There they have all the Docker files from public GitHub repos with 10 or more stars. We filter that down to Docker files that are likely amenable to automated builds. Think of you start a new project and you put it in a single Docker file in the root directory. Those are the kinds of settings where we can hope to pull off an automated build. There are about 30,000 such files remaining when we do that filtering. And due mostly to time and resource constraints, we attempt to build about 20,000, and it's in that reduced sample that we see this 26% failure rate, or about 1 in 4. And that's why we built Shipwright. This is our answer to hopefully fixing all these broken Docker files with an automated technique. So in the coming slides, you'll see a little bit about how Shipwright works, and also some of the results we have from creating and applying this tool. And one of the primary results we have is we actually use Shipwright to submit a bunch of pull requests. So before we go further behind the scenes and take a look at how we built it and some of the results, this is just some of the snapshots from all the pull requests we submitted. And as a grad student that has worked on a lot of projects, but never one where we fixed a bunch of other people's code, this has been a really rewarding and cool experience to produce a tool that helps people fix their broken Docker files. If we take a step behind the scenes, Shipwright operates in 3 phases. The first of which is data collection, and we've talked a bunch about that already. We get a bunch of Docker files from GitHub, we do some filtering, we build a bunch of them, and we end up with about 5,000 that fail to build. We save the logs and a bunch of metadata for those failing Docker files to a database. In step 2 here, this is the human in the loop portion, we're going to try to use some ML and some off-the-shelf clustering to cluster failures, to cluster files that have the same root cause of failure, hopefully. We can't guarantee it, but hopefully they do. And then to give a user these clusters and ask them to do the maybe slightly easier task of trying to figure out, given a large set of broken Docker files, what's common across them and how we might repair them. This is in comparison to giving them all of the 5,000 failures individually and trying to ask them what's up. So we give this to the human in the loop, and they help us produce a database of fixes and suggestions. And then we get to the online phase, and this is where we actually use Shipwright. So this is where we get some empirical results and some data about how Shipwright performs in the wild. You give us a broken Dockerfile, and we check it against this database of fixes and suggestions we built in phase 2. And throughout the rest of the talk, I'll focus mostly on steps 2 and 3 here, on how we do the clustering, and then some empirical results related to actually using Shipwright in the wild. So if all you have is a hammer, so one thing we did with Shipwright was make the decision to use these wonderful, huge, off-the-shelf language models to help us in our task of clustering, but to not spend a bunch of time creating our own architectures or fine-tuning or making new data sets or coming up with 101 heuristics. We asked ourselves, what if we just kind of blindly apply some of the biggest and best language models to these failing Dockerfiles, to the error logs, and see what we can get. So that's where if all you have is a hammer is coming from. If you have these great large language models, what if you just use them? And so we did. We take the Dockerfiles, those are the yellow squares on the left of this slide. We build them, as I've discussed before. We save this metadata, the error logs from the builds. We do some light cleanup and tokenization, basically try to get it to look like a sentence. And then we apply BERT, this large off-the-shelf language model. If you haven't heard of a language model before, just think of this as taking a sentence and giving me numbers. And this is a version of BERT that if the sentences in English were similar, the numbers I get out the other end should be similar. So we apply this to all of these error logs, that maps them into some high dimensional space, and now it's just a high dimensional space with these big vectors of numbers in it, and that's pretty amenable to off-the-shelf clustering techniques like HDVCN. So end to end, you started with Dockerfiles that are broken, you use some ML magic and some standard clustering, and then you ended up with this set of clusters of Dockerfiles that have failed for hopefully similar reasons. That's what we end up giving a user so that they can do the maybe slightly easier task of diagnosing what's wrong with these clustered failures. So here's an example of one of these repairs. You can see here we have error installing bundlers in the log. Bundler requires a certain version, so then we swap out the version number for Ruby. And this is actually the fix I showed you in the earlier example that actually became one of our rules that we have in this fixed database. So I want to leave you all with just 2 quick takeaways. The first of which is that ML can make things easier. We don't do something super fancy for clustering. We actually just apply one of these great, large, off-the-shelf language models, and it produces decent results without any fine-tuning, without our own data sets. I think that idea is translatable to other domains within software engineering. And then last but not least, humans rock. Early on, we realized that something completely automated might be brittle or might not cover a lot of failures. By adding a human in the loop and finding out how to make the task for that human easier, we end up creating a tool that's applicable to more broken Dockerfiles. So now some numbers. It happens that out of the 45 pull requests we submit, 19 are currently accepted, so that's about a 42% acceptance rate, which we're pretty proud of. When it comes to all of the failed Dockerfiles we had, whether they were in clusters or not, when we just take all of the broken Dockerfiles we found and we apply Shipwright, we're able to fix about a fifth of them. So there's comparable tools that do static analysis or like smell detection of Dockerfiles. One I worked on called Binnacle that was in ICSI 2020, and another called Hadolint. And they come up with smells, but smells don't necessarily mean a broken build. So if you're generous and you try to pick out smells that maybe could possibly break the build, you get about a 21% and a 34% detection rate that they think there's something wrong in one of the Dockerfiles in our set. But we have about a 20% fix rate. And also, you might be asking, what about the other 80%? That's challenging. If you write broken C++ and you call make, build, and make install in your Dockerfile, well, your Docker image can fail to build because your C++ is broken. Or if you access a URL and that URL doesn't exist anymore, well, your Dockerfile can fail to build because the environment around you changed. These are interesting areas for future work. How do you handle a changing environment? How do you do like cross-sectional or holistic repair? But they're not the things we focused on. And then last but not least, while we're doing all this work in this cool study and we're trying to build a tool for automated Dockerfile repair, there are developers out there noticing they had broken Dockerfiles and fixing them. So we didn't tell anybody about the broken Dockerfiles. We'd spent several months doing our work and our analysis, and then we went back and just asked how many of these files got updated, and they're now fixed, and there are about 100 of those. And in those 100 files that were fixed, we got about 23 that we can produce an equivalent repair with Shipwright. So that was another nice confirmation that we're producing reasonable repairs. And that's Shipwright, a human-in-the-loop system for Dockerfile repair. Thanks for watching. Check out our artifact. That's the QR code up there. And I hope you all have a great rest of the conference.
Hi again. We are again on air. So welcome back to the Q&A for this session. Today we have Jordan Henkel and Leopoldo Teixeira, both co-authors of this great paper for which you have just seen the presentation, and they are going to answer any questions you may have about the work. Okay? So, yeah, there's a question. So Nazareno Aguirre is asking a question. He says, great talk, and he has a small question. Besides image version issues, what are the most common problems in Dockerfiles that the Shipwright is able to repair?
Great question. I think Leopoldo might have a good answer for this one. I will say that, in the building and the data set analysis and looking at what kind of failures would happen, versioning was a lot. Like, if you just hand sample these files, you see a lot of version-related issues. But Leopoldo, I don't know if you remember some of the
there are not
causes.
only image versions, but typically it's something to do with versioning of libraries or configuration between two different libraries or languages. So commands that will cause trouble when you try to use it while building. So these are, we used an example from image file, but mostly versioning in libraries. That's something that we are able to fix.
Yeah, and I think the versioning stuff, it does get a little subtle because there's like the very obvious version issue, like you go to build and it says something like version mismatch, or I need bundler version 2.4 or whatever. But then there are more subtle things like they change a base image. You're working off of Ubuntu and you're building your Docker image on top of that base and you're using the latest tag. And then they change Ubuntu's package repository in the next version, and a certain package you depended on isn't there. So we see that kind of issue too, where like the world around you changes in kind of subtle ways, and that causes a break in the Docker file. I will say though that there's a lot of issues, that we just see that we don't have great repairs for because they kind of cross boundaries. Like you might have your source code be broken. I'm sure a lot of the failures we have, I didn't benchmark this, but a lot of them are coming from breakages kind of deeper within your repository and not just Dockerfile issues. And that's a really interesting area for further study. But most of our repairs are version-related stuff.
Yeah, also the kind of broken URLs as we've seen. So this is something to add to your question. To answer to your question that you asked, what we are not able to repair. So of course, a broken URL 404 error we cannot fix, but you can at least suggest that something is wrong with that specific comment. So that's the suggestions part of the paper. We focused, of course, on the fix part, which is the most interesting part of the paper and most nicer part. But we can also provide suggestions and pointers on how to fix. But we cannot say that, okay, this URL doesn't exist anymore. How to fix that?
Okay. So thank you very much for your answer. There are no more questions so far. But I think I am going to ask you something. So it is okay. So there's one more question from Nazareno. How do you avoid patches that simply remove lines to make the build succeed?
Yeah, this is another great question. I think this gets into the human in the loop part. I think a really nice thing about this approach is instead of completely trying to automate things, which might run into those kind of like edge cases, like removing a line just to make it work, we do have a human. We focus more on clustering and making it easy for an actual person to look at clustered failures and say, hey, I noticed that in this cluster of 20 failures, I have to change this version number to make them all work. So we don't end up with things like just removed a line as the repair, because an actual human is kind of gatekeeping the repairs that will go into our repair database, right? It's coming from a person. We do a lot of work on pre-processing and clustering and trying to make their job easy. But at the end of the day, there is a person that is kind of the gatekeeper to these changes and these repairs. So that's a nice thing. That also means you do need a person, though, and it's not 100% automated, which is maybe a slight negative, but I think it's a good trade-off.
Okay, so thank you very much for the answer. So no new questions. So I think this time I am going to ask my question. So in one of your slides, I could see that when you are doing the comparison, okay, you have your approach, which is able to fix around 19% of issues, okay? Then there is Vinaco, that it's able to detect, not fix, but to detect 21%, and then Hadolint, that it's able to detect 34%.
Yes.
Okay, so my question is, did you take a look at whether these numbers overlap in terms of the amount of issues that are being either fixed or detected? Do you know if there is overlap or if different approaches are focusing on different types of fixes, or did you take a look at that?
So we actually did not measure any overlap there, but I mean, just off the top of my head, I can think of cases where we might not have overlap right now, but it probably would be a reasonable thing to go to Vinacle and to go to Hadolint, look at those rules that we marked as maybe causing a build failure, and think of the repairs that would maybe fix the possible failure as a source of even more repairs for this tool. So we don't have numbers on overlap. I don't think there's any overlap because we kind of got our repairs for more like in the wild failures rather than here's a list of common smells or something that might be bad for your Dockerfile. But that would be a good source to go back and look at to actually add even more repairs to the database. It's a nice idea.
So then if I understood you correctly, do you mean that your proposal would be that different approaches should be used so that you can combine them and...
Yeah, essentially, I think we should look at the rule databases. So Vinacle learns rules from Dockerfiles automatically. And you could probably go to their list like we did and say, hey, maybe I could come up with automated repairs for some of these situations. In the Vinacle work, we never actually explored repair. So it would be good to kind of revisit that from a repair angle. And then also Hadolint is, again, just a big list of things that are, maybe bad, maybe they waste space, maybe they could break your build. And that might be another source of repairs we could add to our database, essentially. So I guess it's more of a subsumption thing, look at these other sources and try to say, what could we add in?
Okay, so thank you very much.
Yeah.
2.5 minutes to go, but there are no more questions. So if no more questions are showing up, I think that we can...
Nazareno asked... Oh, no, it's the same
No,
one from
it's
before.
not a new... That's what I thought also. At the beginning, I thought, is this a new question from Nazareno? No, it's the same.
It's my bad, sorry.
The one that he asked a few minutes ago. So I guess that I think we can finish here, and you can either take a longer break, or I don't know if later you can join the discussion room and you can continue talking about this great work that you have presented today here. Thank you very much to the authors for being here, and also to the attendees. And to the attendees, I think I will see you in a few minutes after the next video and for the last round of Q&A. Okay, so thank you very much.
Thank you.
Bye. See you later.
See ya.
Bye.
So I guess we